Hello, ladies and gentlemen, Mr. Donnie here with some chemistry. We're going to be looking at gas laws. So our objectives for this video is to use the combined gas law to describe how a gas changes with a change in its environment, and there is math involved, so get excited. All right, so gas laws have to do with pressure, temperature, and volume, and the question is how do these things influence each other? So if I were to change pressure, what's going to happen to temperature and volume? If I were to change the temperature, what would happen to the pressure and the volume, etc., etc. So first law we're going to look at is Boyle's law. So Boyle's law is showing the relationship between pressure and volume. So P1 V1 equals P2 V2. Basically it's saying the initial pressure times the initial volume has to equal a new pressure times a new volume. So as pressure on a gas increases, the volume of the gas decreases. Kind of makes sense. Might not blow your mind, but here's an example. So here, let's say I have 1 atmosphere of pressure in this bottom example, and gas takes up this whole volume, Now, if I were to double the pressure, what would happen to the volume? Well, because we're pushing on it twice as much, it's going to take up half as much space, so the volume goes down. So here's a graphical representation of that. So 1 atmosphere would have a volume of say 10 liters. Well, if I were to double it, then the volume would be cut in half. So you guys did an experiment with this with something that we call a Cartesian diver. So you applied a force on a bottle. It wasn't really from the top. I think you guys squeezed it. But what you did was you applied force, which made the pressure go up. So now what happened inside of the diver was the volume of gas decreased. As a result, because it's not displacing as much water, it was no longer buoyant and it would sink. And if you let go of the squeezing it, if the pressure went down, then the volume went back up and it displaced more water and became buoyant. Second is Charles' law, where it's relationship between volume and temperature. And it basically says V1 over T1 has to equal V2 over T2. So the volume initially divided by the temperature initially has to equal the new volume divided by the new temperature. And basically as temperature goes up, volume goes up. And temperature needs to be in Kelvin. All right, you can't use Celsius with this. So here's a little illustration. Here we got a Bunsen burner heating up some gas, and as it gets hotter, the volume goes up. So graphically, you can see it over here. Or over here, you can see the relationship. If I were to double the temperature, what happens to the volume? It also doubles. So the experiment that you guys did was you had like a beaker, and you had a balloon inside of it with some water, and you heated it up. Now, as it got hotter, the gas inside of the balloon had to expand. The volume would go up. It wants to spread out more. It's got more energy. It's going to expand. So the balloon got bigger. Then Gay-Lussac's law, relationship between pressure and temperature. So P1 over T1 has to equal P2 over T2. Again, remember the temperature has to be in Kelvin. And it's basically saying that as the temperature goes up, pressure goes up. Or if temperature goes down, pressure goes down. So here's a graphical representation of it. Again, if you doubled the temperature, the pressure would double, or vice versa. If you cut the temperature in half, the pressure would cut in half. So you guys did a pretty neat experiment. Hopefully some of you were surprised because I get enjoyment out of seeing you guys get scared. So you heated up a can that had some water in it, and then you flipped it upside down and put it in some ice cold water. So what happened was you heated it up in constant pressure. So it was hot, but it was still 1 atmosphere pressure, room pressure. So then you flipped it upside down and it was sealed, right? And then you cooled it. So, well, if temperature went down, the pressure inside of the can went down as well. All right, well, then the outside pressure is greater and is pushing in on the can because it has greater pressure outside, which crushed the can. It was the air in the room that crushed the can. Pretty cool. All right, so now we have these 3 different laws, and we can combine them into one equation, which we call the combined gas law. And it's P1 times V1 over T1 has to equal P2 times V2 over T2. Remember, the 1s and 2s are saying initially, and then afterwards. So the first condition and then the second set of conditions. So you can kind of see, if you were to ignore parts of the equation, you would still see the original relationship. For example, if you ignored T1 and T2, you would still have P1 times V1 equals P2 times V2, which is this law right up here. Right. So when one thing is held constant, you can simplify the equation. So here's an example. It says a sealed can with an initial pressure of P1 is heated from T1 to T2. What is the new pressure? Well, this sealed can is telling us that our volume is constant, which means that V1 is equal to V2. All right, so if we're looking back at the equation, if V1 equals V2, they cancel out. You can ignore them. You don't have to plug anything in for that because it's constant. It doesn't change. So what you're left with is the equation P1 over T1 equals P2 over T2. So if it's constant, it drops out. So constants cancel out. All right, so let's look at another example. So it says a balloon is with an initial volume of V1 is heated from T1 Kelvin to T2 Kelvin at a constant pressure. What is the new volume? All right, well, if pressure is constant, P1 equals P2, so it drops out. So what equation are you left with? V1 over T1 equals V2 over T2. So now you have a simplified version of this equation. So let's look at some problems with actually some math. It says what volume will 500 milliliters of gas occupy? All right, 500 milliliters, I know that's a volume. If the pressure is changed from 1 atmosphere, so I know that's a pressure, to 2 atmospheres, that's another pressure, at a constant temperature. So I know temperature drops out, I can cross it out. All right, well, let's figure out, is this V1 or V2? It says what volume will the 500 milliliters of gas occupy if the pressure is changed from 1 atmosphere? So we're talking about the initial condition here. And that must mean what volume? They're asking for V2, so that's what we're solving for. It says change from 1 atmosphere to 2 atmospheres. So I know this 1 atmosphere is P1 and the 2 is P2. All right, so let's just fill in our chart. We got P1 is 1 atmosphere. We got P2 is 2 atmospheres. We got V1 is 500 milliliters. So now here, let's see what happens to our equation. The temperature cancels out. And what are we trying to solve for? We're trying to solve for V2. So let's get V2 by itself. We got to divide each side by P2. We're left with P1 V1 over P2 equals V2. Now we can do some plugging and shoving, right? So P1 is 1.0 times V1, 500 milliliters, all over P2, which is 2. And that equals 250 milliliters because we had 1 atmosphere, 2 atmospheres, and 500 milliliters. So atmospheres cancels out, and the units that we're left with are milliliters. Let's take a look at another example. It says a tube of hydrogen gas at a room temperature of 22.4 degrees Celsius. Whenever you see Celsius, immediately just convert it to Kelvin by adding 273 to it. So we end up with 295.4 Kelvin. That is a temperature. And a pressure of 88.0 kPa, so I know that's a pressure. All right, and it looks like it's my initial pressure, my initial temperature. So why don't I fill those in? Got 88.0 kPa, and I got 295.4 Kelvin. What was the new temperature? So they're asking about T2 of the hydrogen gas when the pressure of the tube is at 101.3 kPa. So that is our new pressure. It says volume is constant, so we can cross that out. Alright, so let's take a look at our equation. P1 V1 over T1 equals P2 V2 over T2. Alright, and it says that the volume is constant, so it cancels out. And what are we trying to solve for? T2. So we're going to need to do some rearranging. So some cheats for some basic algebra. If it's multiplying and dividing, it's pretty easy. If it's on the bottom, on the right side, it needs to be on the top, on the left side. So now we got T2 on the top. Now we got to get it by itself. Like I said, if it's on the bottom on one side, it's on the top on the other. So I got T1 on the top on the other side. I got P2. And now I got to divide each side by P1. If it's on the top on one side, it's on the bottom of the other. So this is my new equation set up to solve for the one unknown. So now it's just a plug and chug. I got my T1, 295.4 times my P2, 101.3 kPa. This is Kelvin, all over my initial pressure, which was 88.0 kPa. And I get kPa's to cancel out. I'm going to be left with Kelvin, and I get 340 Kelvin. So that's how you do those problems. That's all I got. Bring questions. I know math, sometimes we need a lot of practice, so we'll be doing that in class. See you there. Bring questions.